In the last segment, we saw how spectroscopy and Balmer's formula gave us the beginnings of some clues about the structure of the atom. We haven't quite seen where those clues headed yet, but here's some more early evidence for the structure of the atom. In 1887, J.J. Thomson discovered the first subatomic particle, and that was the electron. And he also figured out that the mass of the electron was much smaller than the mass of an atom. And so his proposal was what's the so-called raisin cake model of the atom, which was a sphere of positive charge with some negative charges embedded in it. Sort of like the opposite of a modern idea of a metal, where we think about a metal as a positive ion cores and a sea of electrons. So it's kind of the opposite of that. This was one of the first ideas for the model of an atom. And it held for a few years, but then a man named Rutherford came along, and he set up an experiment using a very thin gold foil and a source of alpha particles. And so an alpha particle is simply a helium nucleus. It's 2 protons and 2 neutrons. And it turns out that they get produced quite in a lot of abundance in radioactive decay. And so there's some radioactive source here which is shooting out these alpha particles, okay? And then we collimate the beam with some lead blocks. And all that means is that any alpha particles that aren't going straight through get stopped by these lead blocks. These alpha particles fly through here, and they hit this gold foil. Now, what did Rutherford expect? Well, if the Thomson model was correct, we would expect slightly deflected or not deflected at all, something like that. But it should be pretty consistent, right? Because these atoms in Thomson's model, they're fairly uniform, right? And so whatever we see, we should see some pretty constant deflection. But Rutherford saw something completely different. He saw a lot of small deflections or no deflections at all. Alpha particles passing straight through this gold foil. It's a very, very thin sheet of gold foil. And he also saw some very large deflections. Occasionally, an alpha particle turns around and heads back the other way. This is very surprising. And so what Rutherford concluded here is that actually this Thomson model is not correct. That really we've got a positive nucleus surrounded by electrons. But mostly what do we have? Empty space. There's mostly empty space. Just a positive nucleus and some electrons winging around the outside. It can be a little bit hard to wrap your brain around the scale of an atom. And we've seen pictures all the time that look like this. Here's some protons and neutrons in the nucleus, and here's an electron winging around the outside. And we've seen pictures that look like this, and if you want to make it look fancy, maybe we do a few of those. But what's wrong with this model? What's wrong with this model? Well, there's several things that are wrong with this model. But one big thing that's wrong with this is my nucleus is absolutely enormous. If we're going to draw the nucleus, then we absolutely have to draw it out of scale, right? Even if I was like, okay, I'm going to get rid of that and I'm going to draw my nucleus as small as I can. You probably can't even see that. I know you can't see that. It's still way too big, right? Way too big. So if we want to try and wrap our brain around the structure of an atom and what Rutherford discovered here, let's use an analogy. So here's a picture of Mile High Stadium. Let's imagine that Mile High Stadium is an atom. Well, okay. Then the nucleus would be like a grain of sand on the 50-yard line. I mean, it's just so tiny. It takes up basically no space of the atom. And the electrons are out here in the seats somewhere. What's the rest? Empty space. Empty space, which means that me and you and this pen and your ex-boyfriend, they're all mostly empty space. It's crazy to think about, right? That we think about this as being a solid object, right? It's plastic all the way through. No, it's not. It's mostly empty space with just a tiny little bit of the space filled up with the nucleus. And the electrons, I don't even know if they take up any space at all. In fact, the nucleus only takes up a few quadrillionths of the total space of the atom. All right, let's look at some notation. This is probably a review for most of you, but that's okay. It's important. Let's talk about it real quick. This is the symbol for hydrogen. Down here, we put the atomic number, and this is the number of protons. The mass number is the number of protons plus neutrons, and we use A for it. So A is the mass number. It's also the isotope number, right? So this would be hydrogen 3 is what's described here, and that would be its isotope number, also known as its mass number. Total number of neutrons plus protons. Z is the atomic number, also the number of protons. We use Z for that. And N is the total number of neutrons, which of course must be the mass number minus the number of protons. Occasionally, if we have an ion, we'll put the charge up here. So this right here is magnesium. We see that it has an isotope number of 24, so this is magnesium 24. It has 12 protons, and it is a doubly charged positive ion, as shown in my PowerPoint. Here we have a neutral lithium atom. It has 3 protons in the nucleus, and that means that it must have 3 electrons winging around the outside. Singly charged positive ion has, of course, 3 protons in the nucleus and 2 electrons winging around the outside. Now, of course, when we make an ion, we change the number of electrons, not the number of protons, right? You might think, hey, I'm going to make a positive lithium ion by adding a proton. No, no, no. If you add a proton to lithium, you don't have lithium anymore, you have beryllium. So that doesn't work. So we make ions by adding or removing electrons. And then, of course, isotopes are different numbers of neutrons, but the same number of protons. So here we see helium-3. It has a Z of 2, so that means it has 2 protons. It has an A of 3. That's its mass number, so its mass number is 3. 3 minus 2 is 1. Here we see helium-4. It has a mass number of 4, 2 protons, which means it must have 2 neutrons. We would say that these are 2 different isotopes of helium. Most of the helium on Earth is helium-4, with only trace amounts of helium-3. So isotopes, again, are atoms of the same element with different numbers of neutrons. And so, here's uranium, uranium-238. Most of the uranium on Earth is uranium-238. It's actually quite stable. It's safe, really. Uranium-235 is what you need to run your nuclear reactor. But only a tiny bit of that is uranium-235. There's also trace amounts of uranium-234. Okay. Again, most of you have probably seen this before. Let's do a quick example. How many electrons, protons, and neutrons are contained in the following atoms or ions, and what are the A, Z, and N numbers? Okay, so beryllium -9. Okay, well, what we should do is we should go to our periodic table. And here we see our periodic table. We should find beryllium. Beryllium is right here. And we see that beryllium is element number 4. Therefore, it has 4 protons. It has a mass number of 9. 9 minus 4 is 5. It must have 5 neutrons. If it was a neutral beryllium atom, it would also have 4 electrons. However, it's not. I told you it's negative, therefore it must have 5 electrons. This means it has Z equals 4, A equals 9, N equals 5. How about carbon-12? Let's look at carbon. We've got carbon-12. Well, if we look at our periodic table, we'll see that carbon is number 6. If it's carbon, it has 6 protons. If it has 6 protons, it's always carbon. So we have 6 protons. Its mass number is 12. If there's 6 protons, there's got to be 6 neutrons. And it's neutral. If we've got 6 protons, then we got to have 6 electrons. Okay, so that means we have Z equals 6, A equals 12, and N also equals 6. Great. How about nitrogen 15 plus plus plus? This one's going to be really hard. If we look on our periodic table, here's nitrogen. Nitrogen is number 7 on the periodic table. Therefore, it has 7 protons. This is nitrogen 15. 15 minus 7 is 8. Therefore, there is 8 neutrons. Ooh, if it was neutral, it would also have 7 electrons. It's not. It's triply charged, so it must only have 4 electrons. Great. What does this give us? This gives us Z of 7. A is 15. And N is